All right, so we're going to do an example on strong acid and base titrations. I'm going to start off by first drawing a graph to show how it's represented. So we're going to go ahead and draw the curve. So normally for a strong acid and base titration, you have your acid first, so the curve starts low. And then once it reaches the equivalence point, it increases and it stabilizes again. And normally for the boxes here, and will be 7, and this will be 14. And on your y-axis, we have the pH. And on the x-axis, we have the volume. And this is going to be the volume of the base added. And right here in the middle, at a pH of 7, we have our equivalence point. And it's just a generic graph to show you how strong acid and base titrations work, because we initially start off with strong acid and then have base, which is why the pH increases. So let's work through some practice problems. So we're going to first start off by finding the pH of the following parts. In the titration of 30 milliliters of 0.05 molar perchloric acid with 0.1 molar potassium hydroxide. So the first thing we're going to do is calculate what would be the pH before adding any base, in this case potassium hydroxide. Okay, so there is no potassium hydroxide initially when we're looking at this titration. So the only concentration we have to focus on is 0.05 molar per chloric acid. So we can just use the pH equation. So pH equals negative log ions. In this case, it's going to be pH equals negative log of our acid, 0.05 molar. And that gives us an answer of 1.3. So before we add any base, our pH is 1.3. And if we go back and look at the graph, we can see that it normally starts. It starts like right here, and it's a good estimate of like what we should be finding before adding any base. We should have a very acidic solution. It's only acid in the solution that's present. All right, so going on, moving forward. So how would we calculate something if we add some base? So when, for example, when 5 milliliters of the base, our base is added. So what would be the steps when we're doing this? So now for a strong base analysis, we should always start off by writing off the reaction. So here we have perchloric acid plus our base yielding water and potassium. Right, and you want to go ahead and also, we know the general equation for acid and bases is hydrogen ion plus hydroxide yields water. I'm going to go ahead and just write out the whole net ionic equation to show you where we get that from. So if you were to break these up, you would get CO4 minus aqueous plus potassium plus aqueous plus minus liquid. And you're not going to break water because it's liquid. And this also dissociates into this. So if you remember, like this is your total ionic equation. Here we have a reaction. So now we can go ahead and cancel the spectator ions. And that leaves us with plus minus, giving us water. And this is called our net ionic equation. Right here. So now that we have our equation, just to show you how we're going to be working using the calculations that we get and how we're going to plug it into our equation later. But now we're first going to start off with the numbers given. So in the problem above, we were given 30 milliliters of 0.05 molar perchloric acid. So we're going to go ahead and calculate the millimoles of our acid and base. So we're going to start off with 30 milliliters, multiplied by the molarity that was given to us. And that gives us 1.5 millimoles. And alternatively, you could also change the milliliters to liters to get moles just by itself. But in the end, I'm going to go ahead and divide it by milliliters and cancels out and gives us the molarity. So either way works. And now for our base, we have 5 milliliters of potassium hydroxide. And it was 0.5. 5 milliliters given. That's what we're using. And the concentrations is given as well. And that gives us 0.005, 0.5. So I like to use a table normally just to show the final concentrations that we're going to see. So if I set it up, like using our net ionic equation above that we had calculated, we can do initial, change in final. This normally works for me. You don't really have to use this. You don't. If it confuses you, but generally right here, like you can see, we have 1.5 millimoles. Yeah, I put 0.5 millimoles right here. And we subtract, so we're going to subtract 0.5 millimoles because hydroxide ion is a limiting reactant. That's why we're subtracting by 0.5. And that gives us 1.010. And this is the number we're going to be using to calculate our molarity. Before we do that, we need to calculate the total volume. The total volume is when I was adding up the amount of volume we had for our reactants. So for perchloric acid, every perchloric acid plus the amount of potassium hydroxide we used. So in this case, it's 30 milliliters plus 5 milliliters, giving us 35 milliliters for the total volume. Now to find the molarity of our acid, it's going to be millimoles over milliliters, giving us 1 millimole, which is calculated above, over 35 milliliters. And that gives us a concentration of 0.29 molar. Now that we have the molarity, we can go ahead and plug this into the pH equation. So pH equals negative log. And we already found that, so it's negative log of 0.029 molar. And that gives us an answer of 1.54. So the pH is 1.54. Looking back at what we were answering, so when 5 milliliters of 0.1 molar potassium hydroxide is added, we get a pH of 1.5. And this is more than our initial before adding any, which was 1.3. So we can tell that the pH is increasing as the base is getting added. So I'm going to write that. So the pH is increasing as base is being added. And like a more visual representation, we're looking at the graph. So like I just showed here, like we started off right here with 1.3. So let's say just increased a little bit more once we got the base. So, all right, so now, what if we're given, so what if when 15 milliliters of 0.1 molar potassium hydroxide is added? So what would be the pH then? So we can go ahead and calculate the millimoles for this. So using what we had before, we already have 30 milliliters times our acid concentration, which is 0.05 molar HCl4, giving us 1.5 millimoles before. And now we have 15 milliliters of potassium hydroxide multiplied by 0.1 molar LH, giving us 1.5 millimoles. Now what I want you to notice is that these concentrations are the same. Now what this tells us is that, as we can see here, the concentrations are the same. So right here, the concentration of this is equal to the concentration of the hydroxide ion. And what this tells us is that this is the equivalence point, because the concentrations are the same. And I want you to know that for a strong acid and strong base titration, pH is always 7 for strong base acid titration. All right, so another example we should look at is finding the pH after the equivalence point. So what would the pH be when 20 milliliters of potassium hydroxide is added? So let's go ahead and start the calculations. Can I create before? So 30 milliliters of our acid times 0.041. And that gives us 1.150. So now we're given 20 milliliters. So we'll multiply that by 0.1 molar of potassium hydroxide. And that gives us 2.00. You can see that our concentration for the base is greater than the concentration for our acid. So this is HCl4. So using the equation we had earlier, I'm just going to show you in a table. We got our initial, we got our change, and we got our final. So we got 1.5 millimoles, and we have 2.9 that results. So now hydroxide ion isn't the limiting reactant anymore. So we're subtracting 1.15. And this gives us 0.05 millimoles for this, and 0 right here. And I want you to know this is not for hydrogen ions, it's not our acids. This concentration is the hydroxide ion concentration. Moles of that. So to calculate the pOH, we're going to first have to calculate the total volume. So right here, our total volume is 30 milliliters, plus 20 milliliters, that was with the base, giving us a total volume of 50 milliliters. Now to calculate the molarity, we're just going to do millimoles per milliliters. So it is 0.05 millimoles over 50 milliliters, giving us a concentration of 0.01 molar, and this is for a hydroxide ion. So to calculate the pOH, it's going to be negative log of the hydroxide ion, which is negative log of 0.01, which we just calculated. And this gives us a value of 2. Now this is the pOH, not the pH. So we're going to have to use this equation that we're used to get the pOH. So we move things over. So pH is going to be equal to 14 minus pOH. So pH is equal to 14 minus 2, giving us a pH of 12. So when 20 milliliters of the base is added, we have a pH of 12. And looking back at our graph, this would be represented by right here, because now we have an excess amount of base, which explains why our pH is much greater than what it was before. And these are a few examples to show you how a strong acid and base titration works. One important thing to remember is that the equivalence point for a strong acid and base is always a pH of 7.